that I didn't turn on the recording. So recording is on now and we should be good to go. All right, so this first section, determine the length of the curve. So we have a sine wave on the interval from 0 to 1. So for example, when I say determine the length of the curve, what I mean is if you're measuring along that curve, this is kind of lovely. Okay, a sine curve in the period is 2. So this curve looks something like that on the interval from 0 to 1. So that'd be from there. So 0 to 1. How far would you travel if you walked along the curve? So that actual length. And you could kind of think if that was a straight line, we would know precisely how to do it. We could just measure the length of the line segments. But since it's not a straight line, we're going to have to come up with something using calculus to evaluate that. And then similarly, the area of a surface of revolution, just like those volume problems we did, we're going to want to be able to think about, so this one is, let's see, y equals 1 over x, so a really ugly curve. We'll leave this for later. From 1 to 3, so if I spin that around the x-axis, I get a solid, just like the volume problems, and I want to know the lateral surface area. So what's the surface area of the outside? They're not counting the top and bottom being solid, just the sides. And so we're going to come up with a couple of formulas for those. And once we have them, these are pretty straightforward problems. Okay, so I am going to actually get myself out of there and do a new note. And we'll even give it a name. Let's see. Let's call this arc length. Surface area. There we go. Okay, so arc length is really just how long the curve is from one point to another. So if you guys think, about a straight line, that should be the easiest problem for arc length. So if I say, oops, what the heck just happened? Took myself out of there. If I say find the length of the curve, we're not going to draw it to scale. Let's say this is y equals 1/2 x plus 2. So this is the point 0, 2. This is the point 10, 7. On the interval, let's go 0 to 10. And my job is to find the length of the curve. Okay, yes, Merrick, you are off topic a little bit. But my intention is to drop one of the Newton tests. And that's why you saw one dropped. I usually don't do it until the end of the semester, though. So you'll see all of them in there in your grade, and then at the end of the semester, I'll drop one. So can we all can see that line. Hopefully I calculated my points correctly. I think I did. So can you guys tell me how you would figure out the length of the curve on the interval from 0 to 10? So in other words, how far is it along that curve if I walked from the point 0, 2 to the point 10, 7? How can I figure out how far I went? Think algebra or geometry. Oh, a triangle. I see that now, Merrick. Yeah, we could just say, you know what, let's walk along this side of a triangle and then this side of a triangle. Is that what you were thinking? Okay, use the triangle formula. So let's see, I'm not sure what you mean by the triangle formula. I have a guess. That's 10 units and that's 5 units. What's the triangle formula? Aaron, did you mean the Pythagorean theorem? Okay. The Pythagorean theorem said a squared plus b squared equals c squared if I had a right triangle. And I do. So 10 squared plus 5 squared is that distance squared or that length squared, 125. So my distance is the square root of 125 or 5 root 5. Or if we were calculating 11 point something, I don't know what it is. Square root of 121 is 11 though, so it's 11 point something. Okay, so we know we can get an exact value if our curve happens to be a straight line. Most of our curves are not necessarily straight line. The problem that you looked at on that application sheet was a sine curve. It said, you know, how far do you go if you go from one point to another on a sine curve, and how could we maybe at least estimate it? So think about what we did in the last few sections. For area under a curve, we estimated with rectangles. We chopped things up, we added up the areas of each of the rectangles, and then we took the limit as the number of rectangles went to infinity. For volume of a solid of revolution, we chopped things up. In the slicing idea of it, we chopped things up and we either had discs or washers, and we added up the areas of the discs or washers, and we took the limit as the number went to infinity, and that was an integral again. We're going to do the same thing here, and we're going to come up with an integral again, and we're going to chop things up. But remember, we really just want length, and we know how to find the length of a line. So we're going to chop things up into line segments. So it shouldn't be surprising that in order to do this, we're going to be using this distance formula just like we did for the line segment. We're going to chop things up and look at a bunch of little triangles and add up those little lengths along line segments to get the length of the curve. So let's draw one that's not a straight line. Let's go from 0, 1 to 2, 5. Let's make this y equals x squared plus 1 on the intervals 0 to 2. Oops. So we're going to find that length. Y equals x squared plus 1 on the interval 0 to 2. And we're just going to sort of chop things up. So I could chop in 2 pieces. And if I chopped in 2 pieces, I'd go from 0, 1 to 1, 2, and I'd have 2 line segments. And would that be an overestimate or an underestimate?
An underestimate?
An underestimate. I'm going to be a little bit too low. And I'm not going to go through the calculation because I think you guys can see in the one we did above, we could calculate using the distance formula how far it is from 0, 1 to 1, 2, and then from 1, 2 to 2, 5. We add those together and we're a little bit too low. Now I'm gonna take those out of there. I'm gonna put in a couple more points, and I'm not even gonna label them. If I had 4 points, I could also do the same thing, and you can kind of see that it's still an underestimate, but it's closer. Those line segments are getting closer to the curve itself. And I probably can't even draw 8 of them and have us be able to distinguish on the resolution of my semi-cruddy picture, you know, the difference between where the line segments are and where the curve is. So I'm going to get closer and closer to the curve the more line segments I choose, right? And if I let the number of line segments head off to infinity, in other words, let the number of those little subintervals be infinite, I should get the exact value with some integral. We just have to figure out what the integral is. And to do that, we're going to kind of blow up a picture of what could be any old curve. So we're going from here to here, so like an interval from A to B along a curve. And the curve could do anything. I'm not going to make it too funky. I'll just make it look like a parabola or something similar. And what we're going to do is we're going to chop it up. So we'll chop into little pieces, and we'll try to get that distance plus that distance plus that distance plus that distance. And if I blow up just one of these, then for each interval, I can figure out what this looks like. And I've got some change in x, a delta x, and some delta y, a change in y. And we figured out that to get the distance that we moved, that distance, we had to use essentially our Pythagorean theorem. Distance squared is delta x squared plus delta y squared. So that means that distance or length is the square root of the delta x squared plus the delta y squared. And the problem with this one that makes this one a little bit trickier than what we had with our rectangles and coming up with areas is that we don't have just the delta x in this problem. We have this delta y hanging around that we're going to have to somehow deal with. But we do know that in order to get the total distance, we're going to sum up from k equals 1 to n all of those delta x sub I, or delta x sub k squareds plus delta y sub k's squared and take the square root. And then we're going to take the limit once we figure out what this thing looks like. So I need to get rid of the delta y in this expression. But if I go back over here to my picture, remember slope is change in y over change in x, right? You guys knew that, right? Now, how did we measure slope in calculus? What calculus thing let us calculate the slope of a curve? And this is the slope of the secant line, by the way. How did we measure slope using calculus? It wasn't an integral. What was it?
Wasn't it the derivative?
It was the derivative. We evaluated the derivative at a point. And the mean value theorem, you guys saw that right toward the end of last semester or whenever you had Calc 1. The mean value theorem said somewhere the slope of the tangent line was going to be the same as the slope of the curve or of the secant line. Those things were parallel somewhere along the way if you had a continuous and differentiable function. So as long as your function is nice and smooth, we can find a place in every interval where the slope of the tangent line and the slope of the of the secant line are the same. So what we're going to do with that is we're going to take this little picture and we're going to say, well, that means that somewhere, so some x value in every interval for some x, it doesn't matter which one, because we're going to let those intervals be very small anyway. F prime at that value, they call it like x sub k star. The derivative at that point is equal to the slope delta y over delta x. And we can do that on every one of those intervals. The derivative will be equal to the slope of the line. So the slope of the line, slope of the curve end up being the same somewhere along the way, and we're going to replace that in there. But notice over here in our formula, we just have a delta y. We don't have a delta x. So I need to solve this thing for delta y. Delta y sub k is going to be equal to the derivative someplace times delta x sub k. And if we let all those delta x's be the same, we can drop some of these subscripts. So let's see what happens to our formula. We're only going to do the little development of this for the arc length. The surface area formula is very similar, so I'm not going to develop it too. You can read about it somewhere fun. So we've got our delta x sub k squared plus f prime at some value. They called it with a star. That's not really hugely necessary. Delta x sub k. And all of these things are squared. And now I see that delta x squared in there in both of my terms, so I'm going to factor it out. Still got this big square root, delta x sub k squared, and then a 1 plus delta, oops, not delta, undo, 1 plus f prime x sub k star squared. So it's kind of ugly. You don't have to memorize this, but I think it's good at this point in your classes to see some development as to where these formulas come from. So I'm not going to just sort of throw them all at you. K is going from 1 to n. I've got this expression squared, my delta x squared, so it can come out of my square root. And that means I'm summing the square root of 1 plus f prime at some value squared, and then delta x. But now, since I've got that delta x in there and it's on the outside, this looks like the height of something. So the height piece or the function value is right here. And then the width is here. So this truly is in the form of a nice Riemann sum. And we can take the limit as n goes to infinity. And we know that when we do that, we get the integral. So here's our length formula. It's the integral. My delta x notation becomes dx over whatever that interval was, a to b. And then the thing I have to integrate, though, is the ugly stuff inside the little red oval. Square root of 1 plus f prime of x squared. And the square is extremely important. The 1 plus is extremely important. And the fact that that isn't necessarily a perfect square is extremely important. So this formula can get a little messy looking. And that's why we're going to do most of these problems We'll do most of these guys. We'll do most of those problems using a calculator to evaluate the integral. So the setup is going to be the important thing, and then you can go off and use technology to do the calculation. All right, let's check this formula for our last two problems. So we had two problems we did. Well, actually, one of them we did, one of them we didn't do yet. We found the length of y equals 1/2 x plus 2 on the interval 0 to 10. And then we wanted to find the length of y equals x squared plus 1 on the interval 0 to 2. So for the first one, my function is 1/2 x, was it plus 2 on the interval from 0 to 10. So what do I need? I need f prime of x. That is just 1/2. I need to square that, and I get 1/4. So I need to integrate the square root of 1 plus 1/4 with respect to x from 0 to 2. Oops, not to 2. 2 is the other one. 0 to 10. So this is the integral of the square root of 5/4 from 0 to 10. And that square root is just a constant, so its integral is square root of 5/4 x from 0 to 10. So square root of 5/4 times 10 minus 0. If I do a little simplifying, square root of 5 over 2 times 10 is 5√5, and that is exactly what we had before. So the distance is 11 point something inches, feet, meters, whatever our units are. And that's what we had up above, right? Yeah, 5√5. Now, with that problem, it was easier to just use our Pythagorean theorem, but we don't have that available to us when we don't have a line. So you guys try to set up the integral you would get for our y equals x squared plus 1. So f of x equals x squared plus 1 on the interval, oops, I put that out on 0 to 2. So when you think you have that set up, go ahead and give me a yes in chat to say I've got it set up. And then we'll look through it together. Okay, so it looks like a couple of you are done. We're going to give this about 1 more minute. Notice that I need my derivative, which isn't too bad, 2x. And then I need to square it. So I've got my derivative squared, and then my integral that I'm setting up for length. Oh, and I keep jumping out. I keep hitting my trackpad on here. Okay, there we go. My integral that I've got set up for length is integral from a to b, so 0 to 2, the square root, and the square root is built in here, of 1 plus 4x squared dx. And that's it. Now, in order to calculate this, we do need technology at this point in time. This is a problem that we can use some of our integration techniques that we'll develop later on in the semester, actually in the next chapter. So we'll be able to calculate this exactly by hand. Right now, we don't have that ability. You can try to do this problem by substitution. It won't work. The problem is that the derivative of the inside part, the 1 plus 4x squared, requires an x hanging around on the outside. So we're just going to go ahead, grab a calculator, grab a computer, grab a whatever, and we're going to go ahead and integrate that and come up with an approximation, or maybe even an exact value, depending on what technology you're using. So I'm going to switch my share screen to my computer, and yeah, I'm going to continue. And this one. Actually, not that one. Well, this is okay for now. This isn't the one I want, but I'm going to switch it off to New Mathematica notebook. Hopefully, it will let me. There we go. Didn't want me to switch. Okay, so I'm just going to share a New Mathematica notebook. And what we want to do is integrate. So a couple ways we can do that, but I'm just going to do that. Integrate. And this is a little messy, square root. Remember, you can use that palette, which was a little nicer way to get that information in here. Square root of 1 plus 4x squared. And then close that off. And x is ranging from 0 to 2. And it looks like a messy result. Square root of 17 plus the hyperbolic arc sine of 4 over 4. So this is a sort of mess. Let's just go ahead and get the numerical value, and it will approximate it for us. So it's about 4.65 units from the 0.01. What's the other point? From the 0.01 up to the 0.25. And you can use any 4.65 units. We'll actually go back here and screen share again. You can use any of those. You can use any application you want. So you can use Mathematica. You can use your calculator. You can use, what's this? This was about 4.65 units.
That pad that you were just using, was that when you gave us that one website through the chat, was that to that what you were just using?
Okay, so you mean where I'm writing?
Not this part, but what you were just using with the, was that Wolf?
Oh, with Mathematica. Yeah, that link should be on the main announcement page to the Mathematica download.
Okay.
So, and you can get it free through Delta College. It gives you the instructions. You'll download it, and then you sign in using what they call a license server. So you're using Delta's license server to have access to the application.
Okay, thank you. I tried the one day. I must have been doing it wrong, but I'll try again.
Okay, and it's available. Are you on a PC or a Mac?
Yeah.
Doesn't really matter. But you do have to use it on a computer as opposed to on a tablet.
Okay, thank you.
So, yeah, and remember, you can also use the palette to get the menus instead of typing in like integrate where I did.
Okay.
Yeah, and then I think I showed you how to go off and use Wolfram Alpha too from there, right?
Yeah.
Yeah, okay, good. And then we can get together in Zoom if you're still having trouble getting it to work.
Okay, thank you.
You're welcome. Okay, so there are a couple of arc length problems. I am not going to go through and redo the development of the formula for surface area. I'm just going to give it to you here. So just a little line and I'll give you this formula, or actually there will be two. So surface area, if y equals f of x is revolved about the x-axis. And each of these formulas you can turn around and use along the y-axis as well, but you would need to have x as a function of y. For the arc length formula, it's going to give you the same length. For the surface area, it's a different surface, so it would be a different surface of revolution. But generally on these, you will have the function, so you usually don't need to do manipulation between solving for x. It's usually there. So I'm just going to, as I said, give you the formula. It's a little bit messy looking, but it's fairly close to the arc length formula. So it's still an integral from a to b. There's a 2 pi f of x in here. And then there's the arc length piece, 1 plus f prime of x squared. And this shouldn't be very surprising, because what does 2 pi times f of x look like? It kind of looks like the what of a what? 2 pi, well, 2 pi times radius is the circumference of a circle. So that kind of looks like the circumference of a circle. And if we think about surface area, so if you have some funky curve up here, and you're revolving it about, that outer rim is a circle, and f of x is approximately the radius of that circle. And so 2 pi times f of x would give you the distance around the curve. And then multiplying by that arc length is actually giving us the thickness of the piece. to get sort of that little strip of paint, whatever you would need to cover that. So this is circumference times that little arc length piece gives me the area, surface area for one strip. Then we add them all up and we get the area of the whole thing. So again, this kind of looks a little bit messy, but let's see if we can do this. We're going to do one, we'll do one oddball question. Let's just do f of x equals the square root, which looks a little strange, of 1 minus x squared. And I'm going to go on the interval -1 to 1. So this picture is actually a semicircle. And if I revolve this about the x-axis, what's the shape that comes out of this? What's the solid that we get? You guys know this. It's -1, that's 1, that's 1.
Circle? Oh.
Yeah, but what's a 3D circle? Yeah, say it.
Sphere?
A sphere. Yeah. You just get a ball, a spherical ball. So what this is going to give us is the formula for the surface area of a sphere. And I could even have put this in here instead of having the 1 in there. I could have put an r squared in there and we would have come up with the general formula for the surface area of a sphere. Let's see what happens. So this looks really ugly, but it's going to turn out very nicely in the end. So let's see how messy this starts out. All right, so look at our formula, 2 pi f of x. We know f of x, so we're good there. Then times the square root of 1 plus f prime of x squared. Okay, well, this could get a little bit ugly, but let's do the calculation. F prime of x is 1/2 times 1 plus x squared, oops, 1 minus x squared. Can't change my function in the middle of the game. 1 minus x squared to the minus 1/2 times the derivative of the inside, -2x. So I'm going to go ahead and simplify that. -x over the square root of 1 minus x squared. That's the derivative of that function. But remember, I need to square that thing. So f prime squared, square the top, x squared, square the bottom, 1 minus x squared. Okay. So now let's set up our surface area integral. Integral from -1 to 1, 2 pi times f of x, square root of 1 minus x squared, times this ugly square root of 1 plus f prime squared, x squared over 1 minus x squared. Now, normally I would say, you know what, just pull out the calculator, but this is a case where doing a little bit of algebra will actually make this integral so much simpler that we're going to go ahead and do it. So I need to add underneath this radical, the 1 plus the x squared over 1 minus x squared. And to do that, I need a common denominator. 1 minus x squared over 1 minus x squared plus x squared over 1 minus x squared, 1 minus x squared. Everything else stays the same for now. We're still integrating from -1 to 1. And when I add, notice that really nicely, these two x squareds add up to 0. So now I've got 2 pi square root 1 minus x squared square root of 1 over 1 minus x squared. And again, still integrating from -1 to 1. What happens to those two square roots now? Square root of 1 minus x squared times the square root of 1 over 1 minus x squared. What is that? Very nicely, that's equal to what number? Those guys cancel because they're both under square roots. That's just a big 1, right? That means I am now integrating a constant 2 pi from -1 to 1. So that's 2 pi times x from -1 to 1, 2 pi times 1 minus -1 4 pi square units. So the surface area of that square is 4 pi. And that actually fits because the surface area of a sphere is 4 pi times radius squared. And our radius was 1. So it actually checks with our formula from geometry. But now we can use that if we need the surface area of any strange thing. We got it. All right, let's go back. I'm going to have you guys do a couple of these from this one. Yeah, that's the one I wrote on. Okay, so I want you guys to try, we could do any of these. Let's try number 2. The length of that curve on the interval from 0 to 3. So let's try an arc length problem. Then I think we'll jump up to number 4. Yeah, try number 2. Give that one a whirl and see what you can come up with. You're just trying to set up the length of the curve on that interval. And again, use whatever means you want for your calculation at the end. You don't have to calculate by hand. And if you're really fast and you get that one done quickly, jump to number 4 and see if you can figure that one out.
After we do 2 and 4, are you gonna walk us through them?
Yep, but I want you to get as far as you can in the next few minutes.
What's the first step?
So write down your formula and then look at what you need in your formula.
All right, thank you.
Okay, so start with your, and these are both arc length. So they're using the arc length formula, not the surface area formula. Remember, in that formula, you're going to need the derivative of your function. Okay, so give me a yay in chat when you think you have number 2, and then a yes when you think you have number 4. Funny, Gabe.
And for number 4, right, we're trying to find the original function.
Yes, so number 4, you're working your way backward.
Okay.
Yeah, I gave you the arc length integral. Okay, remember to put a yay and a yes in chat when you have number 2 done, and then when you have number 4 done. So I've got Aaron and Caitlin. So if you, Merrick's good. I like that, Rob. Yes, and yay and maybe. Maybe and no idea. Aaron E says yay and maybe too. Okay, so I think we're probably far enough along that we can take a look at these. So number 2 was length of a curve on the interval 0 to 3. So I'm going to write down my formula. Length is integral from A to B, which we know they gave us that, square root 1 plus f prime of x squared. So that should work. And we could say integral from A to B, integral from 0 to 3. Oops, I need f prime. Let's write it up here so I don't mess it up. F prime is 2 minus 3x squared. So square root of 1 plus parentheses 2 minus 3x squared squared dx. Okay, so does that fit what you guys had, at least so far?
Yes.
Okay, and then whoever calculated this, what did you get for the approximate length? Let's just go 2 decimal places.
I got approximately 9.68.
9.68. Do we have independent confirmation out there? Can anybody confirm that?
Want me to put it in my calculator?
Did anybody else do it? We have another yes. Aaron E, is that a yes? You confirmed that? I think we might be good. Or maybe that was Aaron E's. No, that was his yes on his second one, I think. Yeah, if you gonna recheck. Okay, think so. That looks like I did not calculate it. I just did the setup. Now, actually, we could just go back over here, and I want to show you 2 things actually in Mathematica. So we could set up the integral just like before. Integrate square root. Notice the name of the square root function is a capital S, and that's important. Square root of 1 plus.
You can't see your screen right now.
Oh, shoot, I'm still sharing my other one. Thank you. Let's see, view options. Let's stop the participant sharing. And then I'll share my own. Share screen. Try that one. There we go. Square root of 1 plus, and it's okay, 2 minus 3x squared. Oops. Square root of 1 plus 2 minus 3x squared squared. And x was going from 0 to 3. And this will yell at me if I did something wrong. Something is amiss. Is that our integral? 1 plus. That looks right, doesn't it? Notice
Looks right
that,
to me.
can you guys see my Mathematica screen? Does my integral look right?
Yeah.
Yeah.
Yeah, and notice it just gave it back to me. So what I'm going to do is I'm just going to click this choice of numerical integral, so it will. And now I'm getting 23.78. Did anybody get that instead? 2 minus 3x squared, 1 plus f prime of x squared, 1 plus f prime of x.
Oh, I noticed my mistake. I didn't square the 3x squared.
I was wondering about that, and notice that I almost did that when I typed this in here. So that's a common error that you're going to watch out for. We had it written down, so this should be not 9.68, but somewhere around 23.78. Now, there is another check in case you have your integral set up wrong. There's another check in Mathematica. It's called arc length. So I can actually just tell this arc length. And this time I enter my original function. So my original function was 2x minus x to the third. And again, I have to put that interval in. X goes from 0 to 3. And close that off. And it might just come back with a weird answer again. Notice it just gave me the integral, but I'm happy because my integral matches with what I had come up with on my own. So I know I'm good, and I can say numeric integral, and yes, they match.
What site is this?
This is not a site. This is the Mathematica software that I provided the link for on our homepage. There should be an announcement with the link to Mathematica for Windows, Mac, and Linux. Yes, they make a Linux version. So it's kind of nice because we can double check. All right, so 4. Let's jump down to 4. 4 is sort of going the opposite direction, so we're not going to be able to just calculate on this. I'm going to stop the share on my computer, and I'm going to go back to my iPad. So 4 was this problem. So I know the length of this curve is given by this integral from 0 to 3 square root of 1 plus 16x to the 4th. So this is sort of a reverse engineer problem. I really like this problem because you can't just sort of crunch out something on a calculator. You got to go back and figure out what the original function was. And we're also told that this thing passes through the point 0, negative 36. That's going to be key. All right, so a couple of you said that you got this. How did you figure this out? How did you sort of reverse the process? Here's my formula for arc length. Integral from a to b, square root of 1 plus f prime of x squared. I want to know what f of x is. What does the 16x to the 4th represent?
Your derivative, your f prime, right?
Your f prime squared is the 16x to the 4th.
So 4x squared.
So 4x squared is one possibility. And this did just say determine a function. So that would work. Notice you could also have said f prime of x equals negative 4x squared if you had wanted to. This just says determine a function that does this. We'll take the easier one. All right, we've got f prime of x. How do we get f of x from f prime? What calculus operation?
Integral.
Integral. So I'm going to integrate that. Yeah, and I think, Aaron, I see what you did, but I think you meant you square rooted both sides, right? Aaron, see? So integral of 4x squared is 4x cubed over 3 plus something. Okay. 4x cubed over 3 plus something. How do I figure out the something, the c?
You don't need to, I don't think, do you?
I do, because I said this thing has to pass through the point 0, negative through. Yep.
Oh,
Thanks,
then you
Aaron.
just plug the point in.
Plug the point in. So f of x is negative 36 when x is 0. So my c is negative 36. And now I have my function. It's 4x cubed over 3 minus 36. And you can double check this because you can then now go in the opposite direction. So figure out f prime. you should get 4x squared. Square it, you'll get 16x to the fourth, and then you'll have your integral set up. So that's kind of a nice problem, and maybe not as daunting as it might have appeared at first. All right, let's try
That's
one.
over 3, right?
What'd you say?
That's 4x cubed over 3 minus 36, right?
Yeah, that's really an ugly. Let's see if I can fix that 3. It's kind of ugly. We'll go back to black and there. Yeah, my 3s get messy. All right, let's try just one more of these. Let's try number 5. So this one's asking you to figure out the area of the surface of revolution. So you're going to use your surface area formula this time. And that was integral a to b 2 pi function, and then the same square root that we have in the arc length formula. So this is really the arc length formula plus this extra factor right here. That's what turns it into surface area. Notice you have one more dimension. You've got that f of x dimension. All right, see if you can come up with this one. The hardest thing here is probably going to be calculating the darn thing. Okay, give me another yay when you think you have the number that represents the surface area of this thing. One place after the decimal should be good. I forgot I pulled video down a little bit ago. Did you guys get that for your setup? Two pi times 1 over x times the square root of 1 plus 1 over x to the fourth. And again, the harder part almost, because it's just a pain to enter, but you can enter this on your calculator too. So if you've got a TI-84, just use the numerical integration feature that's in the math menu somewhere down toward the bottom, maybe choice 7 or 8.
Math 9.
I'm sorry?
It's math 9 in the TIE.
9, okay. Choice number 9, if you've got a TI Inspire, CAS, or an 89, you can use the integrate feature and you'll get an exact answer. I'm going to share, I'm going to stop my share and this one. There's the calculation on Mathematica. Notice the messy form, -1/9 pi times negative 9 root 2 plus the square root of 82 plus 9 times the hyperbolic arcsine of 1 minus 9 times the hyperbolic arcsine of 9. So that's kind of a mess. There it is numerically. You could also do.
Did we even learn hyperbolic yet?
We have not. They're coming up. But remember, I told you that. I told you some of these functions are things that we have not learned how to integrate yet, and that's why we're just going ahead and are using our calculator. So even some of the simplest functions, when we calculate their arc length, they lead to a really messy integral. So we're going to do these calculations unless they come out very nicely by accident or just because of the nature of which problem they are. We're going to go ahead and do these calculations using our calculator or using a computer. So quick show on this one. The original was 1 over x, and we wanted the arc length from 1 to 3. And sometimes it flips us out to these oddball functions, this gamma function and a hypergeometric function, but let's try numerical value. Uh-oh, something's amiss. Did I change my function? It was y equals 1 over x.
I got 1.2 and I plugged in my calculator, but maybe I did it wrong.
1.2 isn't either of my answers, so
I didn't multiply by 2 pi yet, though.
Oh, okay. But if I'm using the arc length function, I don't need to. Oh, that's why I got a different answer. This is the arc length. This isn't the surface area. I don't think I have a surface area formula. That would have been arc length. So this can actually, let's just kill this because that doesn't fit that problem at all. I forgot we were doing surface area and not arc length on this one.
I got 7.6 if anyone else got that.
That's, if you look at my screen, that's what I got.
Yeah, I just seen that.
Yep. Okay. So the 7.6 looks good. And so that would be 7.6 square units. Squared. Okay, so that's not too bad. All right, and I think it's just about 11:30, and we are, let's save that. We have hit examples from arc length and surface area. Our next topic, which was really supposed to be today, but it's kind of, I don't really want to start it with just a half hour to go. So, I would rather you guys look at the problems first. So make sure you look at the physical applications section before next time, even if you just try to do a quick read through and maybe try 1 or 2 problems, just so you can see what kind of thing they're looking at there. So some of the problems are going to be calculating mass, others are going to be calculating work done when an object is moved, maybe when a spring is stretched. So work, and then there'll be probably some force problems that we'll look at as well. Force and water pressure type problems. So it's sort of an application type day next time. Do you guys have any other questions you want to ask about? I will upload this notebook so you have some examples that show you syntax to use for integrate and for arc length, for those functions, so you can see what you need to put in there if you want to use Mathematica for your calculations. Stop that share. All right. Any other questions before we sign off for today? We good? I will see you on Wednesday. Make sure that if you want to ask questions or see some arc length problems that you look at, or physical application problems, that you look at those before you come on Wednesday, because that'll be helpful for us. Okay, cool. I'm going to end for all.